Let me show you one of the mightiest tools in mathematics, the Camel principle. I'm dead serious. Deep down, this tiny rule is what makes many methods and theorems work, ones that you use every day. Here is what it is, how it works, and why it is essential. First, the story. The old Arab passes away, leaving 17 camels to his sons. Half of his fortune goes to the eldest son, third to his middle son, and ninth to his smallest. This is a problem, as they cannot split 17 camels into a half, a third, and a ninth without cutting some of them into parts. So they turn to the wise neighbor for advice. The wise man says, "Hold my camel," and solves the problem by lending one to the boys. Now the stable has 18 camels. The eldest son takes 9 home, while the middle and the smallest son leaves with 6 and 2 camels, as their father wished. The wise man takes his camel back, and everyone is happy. Yes, I know. A half plus a third plus a ninth equals 17/18, which is an 18th short of 1. But this is how the old folklore tale goes, and it teaches us an invaluable lesson beyond basic algebra. The lesson: adding and subtracting the same quantity doesn't change the equality, but can help in the computation. One of my professors used to call this the Camel principle, which stuck with me. You might call this fancy addition of zero or something else. Mathematically speaking, we say that x equals x plus y minus y. You might call it trivial, but this trick enables so much. I'll show you a basic example: solving quadratic equations. Here is an example of a quadratic function whose graph is a parabola. What we are interested in are its zeros, that is, the points where the graph intersects the x-axis. Algebraically, this is equivalent to solving the quadratic equation a times x squared plus bx plus c equals 0. Here is the famous solution formula, which is one of the few things everyone remembers from high school. This formula is obtained with the help of the Camel principle. Let's see how. First, we factor out a from the quadratic expression to set up the fancy addition with 0. Now, our goal is to use the famous algebraic identity x plus alpha squared equals x squared plus 2 alpha x plus alpha squared. We can find what alpha should be by matching the coefficients of x, getting that alpha should be b over 2a. As the square of b over 2a is not there, we apply the Camel principle to conjure it up. This is called completing the square. Now we can apply the previously seen algebraic identity to isolate x into one term. Since the product of two terms is 0 if and only if either term is 0, this move leads straight to the solution formula. Let's see another example. If solving a quadratic equations seems too basic for you, let's talk about the chain rule, the formula that expresses the derivative of composite functions. First, let's look at the concept of derivatives, the main engine behind mathematics, physics, and optimization. Let's use the already familiar quadratic function for demonstration. Geometrically speaking, the derivative of the function f at point A is the slope of the tangent line to the graph at A. In mathematical terms, the derivative is defined by the limit of the so-called difference quotient f at x minus f at a over x minus a as x goes to a, if the limit exists, but let's suppose it does. How would you compute the derivative of a composite function? This is a quintessential question. Without this, you don't have backpropagation, gradient descent, and thus neural networks. At least until someone finds a clever alternative, but that will take a while. What helps us here is an alternative version of the Camel principle performing a similar feat, multiplying and dividing with the same quantity. This doesn't change the equality either. So, Let's look at the chain rule once more. By sneaking the term g of x minus g of a into the picture via the multiplicative Camel principle, we get that the derivative of the composite function is f prime at g of a times g prime at a, which is known as the chain rule. This is what we use to perform backpropagation, enabling us to train neural networks in a reasonable amount of time. Alright, one last example, something which I like to call triangle inequality trick. This is my personal favorite, something that I've used on research level problems. It's a well-known fact of planar geometry that if you have a triangle of sides A, B, and C, then the length of any side is less than the sum of the other two. Mathematically speaking, C is less than A plus B. This is known as the triangle inequality. This holds true in general vector spaces as well. There, if we have vectors A, B, and their sum A plus B, then the triangle inequality applies to their norm, that is, A plus B norm is less than or equal to A norm plus B norm. In fact, the triangle inequality is the part of the definition of a norm. Here's the trick that I've seen and used countless times. If you need to estimate the norm of x minus y, that is, the distance between x and y, you can sneak in an arbitrary vector v via the Campbell principle and estimate the distances from this v via the triangle inequality. If your choice of v is appropriate, x minus v norm and v minus y norm can be easier to manage. So, where is this used? Off the top of my head, 3 results come to mind. That the limit of uniformly continuous functions is continuous, that Cauchy sequences and convergent sequences are equivalent in the set of real numbers, and the Banach fixed point theorem, but there are many more. These are all worth their own videos, so I'm not going to go into the details, but feel free to look into them for further research. There we have the Campbell principle, one of the most powerful tricks in mathematics. It works so well because instead of finding the best strategy to deal with an expression, we change the game to make our strategy work. Thanks for watching and see you in the next video. Cheers, Tivadar!